All right, so we have our liquidus line here. As you can see where my cursor is. And then we have our solidus line below here. And then we have temperature in degrees Celsius on the left, y-axis here. And then on the right here, usually we have temperature in Fahrenheit. This one is not important to us. What is important here is in degrees Celsius, because that's the unit of measurement that we use. Then when you come down here, we're just given the composition weight percent for nickel. So what this means is that if weight percent for nickel is 20 here, it means that for copper it's 80. If for nickel here it's 60, this x-axis, so it's showing the weight percent for nickel. So if nickel is 60, automatically we know that copper is 40%, 40 weight percent, and so on. So what else is new here? Oh, we have the intermediates here with the alpha plus beta. And we have the alpha and the beta. So let's come to point A. Okay, Fales. We have our point here. What state is our point A here?
Hello?
In what phase is our point A?
Solid phase.
It's in the solid phase, thank you. And the point B?
Point B. Non liquid phase.
Look at it again. Point B, where is it sitting? It's in the alpha plus liquid, the intermediate phase. It's in the alpha plus liquid phase. Thank you. You can mute your mic. It's in the alpha plus liquid phase. Okay, so from here, point B, we can easily determine what temperature it's at. Richard, can you help us determine the temperature for point B? I've put this line here just to help.
It's at 12,500 degrees.
That is
one. Please go ahead. I can't. Please kindly repeat yourself.
1,250 degrees Celsius.
Yes, so roughly, thank you. Roughly 1,250, not 12,000. I think I added 12,000 at first. It's 1,250 for the 1,300. So in between, somewhere in between 1, 2, and 1, 3. So 1, 2, 50, roughly. Okay. Seems like touching the hang of it here. And for component A is here. What's the temperature, Eunice?
Doc?
Yes. Can you please give us the temperature for component A? At point A, sorry, not component A, but at point A. Our solution at point A. Yes, what's the temperature?
The temperature is at 1,100.
Okay, 1,100. Thank you very much. You are correct. So basically, we're able to tell, the phase diagram will even help us to tell, isn't it? To say at this temperature, what do we expect? Okay, we can just by simply looking at the phase diagram of the two alloys. So copper and nickel, this is the phase diagram. So if today you are told to make an alloy of copper and nickel, this is what you're going to use to tell at what temperature, what microstructure to expect, or what compositions to expect. What else can we pick from here? I think let's move forward. I think we'll have better, more illustrations as we go. So in one component system, melting occurs at a well-defined melting temperature, isn't it? So if you have just copper, you know the melting point for copper is, for example, 1,300. So you know that when you are heating it and you reach to a temperature of 1,300, you're expecting it to begin to melt. However, in multi-component systems, melting occurs over a range of temperatures between the solid dust and the liquid dust lines. So when you are dealing with two binary, that's why you have the intermediate phase, isn't it? Because you have different melting points there for your components. In a one component system, you won't have that intermediate phase because you just have one component. When it's melting, it begins to melt really, and you understand that it's melting now. But for the binary and the more than two component systems, your melting is happening over a range of temperatures between the solid dust and liquid dust lines. And the solid and liquid phases are at equilibrium with each other in this temperature range. Okay, so more about this. So now we look at the microstructures. Let's begin now to slowly understand what to expect with our microstructures. So let's pick this point, for example, here. You see where my cursor is? There's a point here. So this is in the liquid phase. So with the liquid phase, when you get a liquid and put it under the microscope, what are you going to see? You're basically just going to see this. And others would put dashes inside to depict a liquid, but it's not important. But basically, it will just be this, so be nothing. So your microstructure here is basically nothing. There's nothing inside. It's a liquid. Then when you come here to this point here, this point is in the alpha plus L. It's in the intermediate phase. So in this phase here, what you are having now is, as you are cooling. So the other assumption, by the way, with the phase diagrams, you need to understand is that we are moving from high temperature to low temperature. Okay, we're moving from high to low. So we're basically cooling. So now during cooling, why we do that is because we attain our metals. Most metals are attained at a high temperature, isn't it, from the ores, or in the furnace, or in whatever vessel you're using. It's usually at high temperature. Then now that's when you begin to cool. So from here, we are now moving downwards. So from this high temperature here, as we begin to cool, what happens now? Solids begin to form in this intermediate stage. Then, so it means that we are, solids are beginning, so crystals are beginning to form, okay? Crystals are beginning to form in this stage here, such that by the time you hit the solid dust line, beyond this solid dust, any point beyond it, you have a complete solid. So while you're in the solid dust, in the alpha plus liquid, the intermediate phase, this is what you're expecting to see. As you can see here, you have your nucleation happening, or your joining of the different crystals, right? They're mounting up together and forming groups. This is what you have here. You have your solids now here forming up, and you have your liquid also still present in the solution. And once you go beyond the solid dust line, it means that you have a complete solid. So any part here below this line, here, here, there, here, everywhere here, is solid. So when these ones, as they're nucleating, they're expanding, isn't it? More crystals are forming up and inclining themselves to these various groupings of crystals. In the end, what happens? You have this one now became this part here, and so on and so forth. So you have this structure here with the grain boundaries. Remember, we looked at grain boundaries. So this group of crystals were forming in a similar fashion, in a similar pattern. These ones also were in their own pattern. This one was in their own pattern. So as they grow, as the liquids is continuing to solidify and joining themselves to the different structures near them or patterns near them, in the end you have this now. When they join together there, you have the boundaries there, differentiating the different types of arrangements, crystal arrangements, or what is known as a polycrystal solid solution. So this point here. So from there, from this point here, no solids, then here they begin to form, and finally here you have a complete solid with no liquid present in it. So this now is being done. So what is happening? What is changing here? As you can see, these points are in a straight line. What does it mean? It means that the only variable that is changing here is temperature. Composition is not changing. So composition has been the same from this point right up to the time that it's solidified. So 40 weight percent of component A through and through. Any questions here? Okay, we'll still continue looking at this. We're going to the number of diagrams of similar fashion. So for given temperature and composition, we can use phase diagrams to determine the phases that are present, like you saw in the previous diagram, isn't it? We determine the liquid, the alpha plus L, that is the intermediate phase, plus the solid phase. We're also able to tell the composition of the phases, as well as the relative fractions of the phases. The fractions, that is from the weight percent there, you're able to tell if, okay, if nickel is 40%, it means that copper is 60 in the case of the binary system. Also looking at here binary. So finding the composition in the two phase regions, you locate the composition and temperature. So now we're going to, oh, sorry, I forgot to mention one thing. Using the tie line or the isotherm. This, let me show you. This is the lever rule, what is known as the lever rule. So when you want to know the composition of this particular point here, you want to know what is the composition at this point of the solids and the liquids at this point. So what you do is you get a line, get a ruler, and you draw a horizontal line passing through these points. And where it touches the liquid dust and the solid dust lines, you drop it. Okay, you drop the lines where they're touching the liquid dust line and the solid dust line. You drop them there and you get your compositions there. You have 20 and 60. Remember here we have 40. So for you to know the solid part, okay, so in this case, liquid is on the left side. I would say the liquid is on the left. The L is on the left and the alpha is on the right. I'll tell you an easy way to determine this. So if you want to know the solid parts, this solid part, the composition, what do? You do the opposite. So alpha is on this side, isn't it? The liquid is on this side. So you get the left hand. So you get this composition divided by the overall composition. So it means you're going to have, when we're going to see the formula there ahead, but you are going to have the numerator and the denominator. So in the numerator, just imagine there's a big line there. So in the numerator, you're going to have this point. So you're going to have 40 minus 20, this region here. 40 minus 20 divided by the overall, which is 60 minus 20. So the numerator you have 40 minus 20, and the denominator you have 60 minus 20. So 40 minus 20 is what? 20. Divided by 40 minus 20, which is 40. So you have 20 over 40 there. And when you divide, that is the composition that you're expecting of the solids. Then if you want to find the composition of the liquids is on this side, so it's the opposite. You're going to get now this portion here divided by the overall portion. So this portion here is what? It's 60 minus 40. 60 minus 40 divided by the overall line here, where it's touching the solid dust and the liquid dust line. So this is 60 minus 20 in the denominator. Numerator will be 60 minus 40 divided by 60 minus 20. That's how we solve for it. Okay, so maybe a closer way to see it. If you want to depict it. So this is where our 40 was. And this is the solid dust line. So for solids here, and the liquid dust line is there. This is our tie line. So like I said, if you want to find the solids are this side, you get this line, this distance here, divided by that distance here. If you want to find the solids, the amount of liquid, you get this distance divided by the overall distance here. Okay, so this is basically just the instructions, and then you read this by yourself. I'll give you this presentation. So the lever rule is a mechanical analogy to the mass balance calculation. So it's just similar to the way we calculate for mass balance. The tie line in the two-phase region is analogous to a lever balanced on the fulcrum, just like that's why it's called the lever rule. That's basically more like a balance. So what are the conditions here? All material must be in one phase or the other. So you have this alpha, so weight present for alpha and liquid, which is equal to 1. So the alpha and the liquid should be 1 all the time. And the mass of the component that is present in both phases equal to the mass of the component in one phase plus the mass of the component in the second phase. So you get, I recommend a Callister for this. It really explains them in detail, step by step. I'll just go through. You may not be able to, maybe in case you're not able to catch it at the pace at which I'm going, you can simply just go through Callister. It's a really good step-by-step illustration of this formula. So number 3, solution of these equations gives us the lever rule, and you have your formulas over there. Anyway, what I explained, if you got it, is basically what this is. So another example here. You have our tie line here, and you have our point B over here. So where your solid dust line is touching, where your tie line is touching the solid dust line when you drop it is our C alpha, okay? Concentration at alpha, this one here, 42.5. Then where our point B is lying is our C0, okay? C0 is 35, as you can see here, 30, 35, and 40. So it's somewhere in the middle here, it's 35. Then where you have the liquid dust line there, where your tie line is touching this line, the liquid dust line, when you drop it, this is known as the CL, concentration at the liquid dust. So when you look at this is 30, this is 40, it must be 30 something, less than 35 though. So it's 31.5. There it is. Just one more, please. All right, sorry about that. We continue. Okay, so these distances here depicted as R and S. So for mass fractions, the WL, the L is supposed to be index actually. It's S over R plus S. So S divided by R plus S. So like I said, for liquid, you get the opposite. Liquid is this side, isn't it? So when you want to find out how much liquid is there, the composition of the liquid, you actually get the opposite. You get this distance. So which is S here, okay, S divided by the overall distance. The overall distance is R plus S. For you to find the amount of solids, you get this one. So solids, you alpha will be this side, right? But you get this one to find the solids. To find the liquids, you get this. So to find the solids, you get R divided by overall distance, which is R plus S. So R in or, what is it called here? So it's the, for the first one, where you're finding liquids, it's simply what? This distance S is what? It's C alpha minus C0. C alpha minus C0, that would be your numerator, divided by overall. So overall is C alpha minus CL, okay, divided by C alpha minus CL, which will give you 0.68. That's for liquid. For solids, if you want to find solids, then what do? It's for solids, we said it's this distance. R divided by R plus S. Or R in this case is what? C0 minus CL. C0 minus CL divided by overall distance, which is C alpha minus CL. C alpha minus CL, which will give you 0.232%. So when you take this in percentage, it means it's going to be 68% and 32%. What does it mean? It means that at point B, so point B here, the liquid is 68%, okay? While the solids are 32%, which also somehow makes sense, isn't it? It's closer to the liquid. That's why you're just moving, you're just coming out of the liquid phase and making your way this side. So meaning it's more of liquid than solid. However, if you got a point somewhere a bit lower, for example here, and you had your tie line here, you find that at this point here, you find that you have more solids. This value will be higher than this one. It means that you have more solids, which logically makes sense because you're approaching the solidus line, meaning now your solidity should now get more and more defined, such that by the time you're touching this line, or your metal is touching that line in terms of temperature, the temperature is dropping to that line, it means that it's almost in complete solid state. So a question would be, what happens on this line? How does the structure look like? And we'll look at that as we go forward. Any questions up to this point? Charles, is it clear?
Yes, madam, it's clear.
It's clear.
Sorry for joining the class late.
It's okay. Who else do I have? Mika. I hope I pronounced your name correctly. Tavo, are we on the same page?
Yes, madam, we're moving on the same page.
Sorry, yeah, that's Mika, that's me, Kunda. Sorry, I'm using my daughter's phone. So then I didn't realize the name is Mika.
All right.
I'll change that now.
Understood.
Okay.
All right, so development of microstructure in isomorphous alloys. So we're now going to look at the development of the microstructure in the isomorphous. Remember, isomorphous is what? Solid solubility, where you have two components dissolving into each other without limits. And what's the other condition here? We're looking at the equilibrium or the very slow cooling. Equilibrium or very slow cooling. Like I said, in industry, we don't do equilibrium because it takes very long. It takes an awfully long time. No one has the time to wait for days just to a simple metal. but we still look at it because of the way it helps us, it gives a more defined microstructure development, unlike in very fast cooling or dynamic equilibrium cooling. Okay, so we come now, we've got points A, B, C, D, and E, and we're going to look at each and every one of these points in detail. So we begin with point A. Oh, wait, before we do that, we need to understand what are we looking at. This is nickel and copper, so this is weight composition for nickel. Okay, sorry, this is for nickel, so not nickel and copper, but this is for nickel, just one component here. And we have temperature here on the left. In degrees Celsius. Okay, then we have weight percent for nickel here. So now when your nickel is cooling, so we begin at this point here. Let's start with 1,300 roughly. So you have a liquid here, and what's the composition? When you draw this line down here, you get the composition here. What's the composition roughly? Mutumba, can you tell us what the composition for nickel is, the weight percent? Anyone to help Mutumba?
35.
35 weight percent, exactly. So you have the 35 weight percent, 35 nickel written inside them. So this is your microstructure A. That's liquid. They are not solid, so that's why it's just empty. L. Empty. There's nothing inside because it's a liquid. So under the microscope, you just see. So we move to point B. Point B is right on the solid, on the liquid dust line. Sorry, it's right at the boundary line here, the liquid dust line. So what are we beginning to see at the liquid dust line? What we're beginning to see is the formation of crystals or the formation of solids beginning to happen, isn't it? So you can see the peaks there. So how do we know the composition as well here? We still do the Tyler, the Liveroo method, the Liveroo. So if you draw a line there where it's hitting the solid dust line, it's hitting the solid dust line at 46. If you drop this line down here, it comes to like 46% here. Okay. So you have our a solid slowly forming there, and then you still have your liquids well in place. So it's more of a liquid than a solid at this point. So when you come to point C here, when you come to point C, what's the microstructure? The microstructure is here. You see your alpha, isn't it? Your alpha particles there, they are nucleating or they're expanding. So meaning more crystals are becoming attached to these separate groupings of crystals. So initially you had the tiny, tiny ones. Now they're actually expanding. So this is what you have here. You have your liquid, remember, and in the intermediate phase. So you still have your liquid well placed, but then you have also your solid parts also well forming there. So you have it's saying 43 alpha because when you put a tie, when you draw a tie line here and you drop this one here, it's giving you 43. That's why you have 43 depicted here. So meaning again, how do you find for C? How do you find the amount of liquid? You use the lever, isn't it? You drop. Remember that method we used. You drop this line here where the tie line is touching the liquid dust line. You drop a vertical line to your x-axis. Same here. That's for point C. 43. So you have 43 here, and you have a 32 there. So meaning if you want to find the amount of liquids, what do? It's this. You're going to say 43 minus 35 divided by the overall distance, which is 43 minus 32. That's how you find the composition for your liquids. Composition for your solids is this part here, so which is going to be 35 minus 32 as your numerator. Denominator will be 43 minus 32. That's how you find your composition for the solid particles for C. Moving on to D. D is on the solidus line, the line that is separating the solid phase from the intermediate phase. So your solid line here, what does it mean? It basically means that you have a much greater portion of your microstructure composed of solids than liquids. As you can see here, because we are beyond this point, anything beyond this point means we are completely in a solid state and there's no liquid whatsoever. So by the time any point below D, any point, even just the next millimeter there or fraction of a millimeter beyond this line, you are already in a complete solid form. You're going to achieve this. This, you achieve it here, you achieve it there. Anywhere here below this line, you are achieving a complete solid. Okay, I hope I'm clear then. So even if E, we shifted it down here, we'll still achieve this. So at E here, what's the composition again? It's still 35% nickel, and this is after nucleation. Now, when these crystals have expanded, what happens? They'll join together, and then they'll have these boundaries between them, between the different arrangements of the crystals. And there you have your microstructure for the point E, which is in the solid phase. So an exam question comes where you have these points, and you'll be told to draw the microstructure. I'm sure that's not very hard. So you'll be given these points in the exam, for example, and you ask, say, draw the microstructures and temperatures for the following points. So you start point A, you draw a line there at what degrees Celsius. This is a microstructure. B at this is a microstructure. Sometimes you'll be asked to find the composition, okay, of the solids and the liquids at these different points. That's where now you're using the lever rule for the tie line there, drawing the tie line and calculating for the different compositions of the solids and the liquids.